Hello, today we are going to discuss Lewis dot diagrams, which also sometimes are known as electron dot structures. So we are going to begin this discussion by examining three different elements, which I have drawn Bohr models for. So we have fluorine. Fluorine has 9 total electrons. You can find that out by looking it up on the periodic table and seeing that its atomic number is 9. So that means it's got 9 protons in the nucleus as I've drawn, but what we're really concerned with is the electrons. So we put, we put 2 electrons in the first shell here, and then that shell is full. So then we have to move on to the next shell, put our 3rd, 4th, 5th, 6th, 7th, 8th, 9th electrons in the second shell. Now remember, every shell outside of the first shell can hold up to 8 electrons. Valence electrons are the electrons in the highest occupied energy level. So in this case, the highest occupied energy level for fluorine is that second energy level, second ring. And if I count up, there's 1, 2, 3, 4, 5, 6, 7 valence electrons in fluorine. All right, for neon, we go down here. Neon has a total of 10 electrons, so it's got 10 protons in the center. I draw my 10 electrons. I put 2 electrons in this first energy level, first ring, and then I put 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second shell, because that gets us the total of 10 electrons. There would be 8 valence electrons in neon. Now, we call 8 valence electrons an octet of electrons. And octets of electrons, or full outer rings, mean that the atom is going to be very stable, or your textbook sometimes calls this inert. Next, we're going to move on to the 11th element on the periodic table, which is sodium. So sodium would have 11 protons in the center of its nucleus. It would have 2 electrons in the first shell, which is full. Then we would put 8 electrons in the second shell, which would then be full. But 2 plus 8 is only 10 electrons, and we need 11. So we would put the 11th electron right out here in the third shell. And so that would mean that sodium has 1 valence electron. All right, now these valence electrons are special because the valence electrons are the only electrons that can be gained, shared, or lost when forming chemical bonds. So the Lewis dot diagram is basically an abbreviated form of this whole Bohr model so that we can see what's going on and what this atom has to offer as far as bonding goes without having to draw the entire Bohr structure. So if I wanted to write the Lewis dot diagram for sodium, I would write a capital N and a lowercase a, because that's the symbol for sodium, and I would put 1 dot on it to represent my 1 valence electron. It doesn't really matter where you put that 1 dot. You can put it on the left or the right, top, bottom. It just needs to be a capital N, lowercase a, with 1 dot to represent its valence electron. All right, let's try the Lewis dot structure for neon. Well, the symbol for neon is capital N, lowercase e, and neon has 8 valence electrons. So I'm going to draw all 8 electrons here. That would be the Lewis dot diagram for neon. So it's neon with 8 dots. Now I do want to point out, these are supposed to go on the 4 sides of the element. These are not like lightsabers where you draw all 8 of them in a row. That's bad. That's not a correct Lewis dot diagram. All right, fluorine would be a capital F for fluorine. We would put 7 dots around it because there are 7 valence electrons. Now, we said that in order for an element to be stable, it has to have 8 valence electrons. So if I look here, fluorine is nearly there. It has 7 electrons around it. But in order for it to be stable, we need to add an electron. And if we add an electron now, fluorine is going to have a full 8 dots around it. But that's not regular fluorine anymore, because instead of having 9 total electrons, we now have 10 electrons in that structure. There are still only 9 protons because it's fluorine and we haven't messed with that. So if we look here, that means we have 1 more electron than we have protons. So this is F with a -1 charge on it because it has one more electron than it has protons. This is now an ion, and we would call it the fluoride ion because the "ide" means that it is negative. Neon does not need to gain or lose any electrons in order to be stable because it already has a full set of electrons. Let's take a look at sodium. So if we look here, look at the diagram of neon and then look at the diagram of sodium. The only difference between neon and sodium as far as electrons go is this outermost electron. All right, so we've got some options. In order for this to be stable, I could pick up 7 more electrons. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yes, so I could add 7 electrons in order to be stable. Or what about if I did this? What about if I just lost that one outer electron that sodium started with? And if I lost that one outer electron, then let's take a look here. This diagram looks remarkably similar to the neon diagram because now it's got 10 total electrons and the outer shell is full, so lose an electron. All right, so losing 1 electron would make sodium stable, and if it loses 1 electron, then that means instead of having 11 electrons, it now has 10 electrons. But it still had 11 protons. So that means that now sodium is Na+1, and this dot that it used to have in its Lewis dot diagram, we should erase it and not include it because it has been lost. So, pardon me, our ion would look like that. Sodium would be Na+. You can write it as Na+1 if you want to, but the 1 is kind of implied. And we would call that sodium, but we would have to call it sodium ion so that we knew that it has a charge instead of being elemental sodium. You don't change the ending to positive ions. Remember, cations are positive ions. So as you read through section 7.1, it does discuss some patterns and some predictable charges. Remember, cations are positive ions. Metals tend to be your cations. And cations form because they lose electrons, which makes them more negative or more positive, because electrons are negative. So as you lose electrons, you're going to become more positive. So I can tell you that group 1 is called the alkali metals. And all of the alkali metals have 1 valence electron. That's why they are grouped together. They will always make +1 ions. So sodium is Na+, potassium K+, lithium Li+. Group 2 elements. Those are, as we learned in the last chapter, called alkaline earth metals. They, instead of losing 1 valence electron, have 2 valence electrons, so they will always make +2 ions. So examples of this, Mg is Mg+2. Calcium is Ca+2, and you can just keep going down the column. Now, group 7, which is the halogens. The halogens all have 7 valence electrons, and they need to get to 8, so they will always want to gain 1 electron, which will give them a -1 charge. So fluorine is F-, fluoride. Bromine becomes Br-, I becomes I-. Group 6, which is the oxygen family. The oxygen family has 6 valence electrons. I guess I should say group 7A, group 6A, or you could call this group 16, group 17, depending on how you're counting. But if they've got 6 valence electrons, then they would need to gain 2 electrons to become stable, which means that they are going to have a -2 charge on their ions. So oxygen becomes O-2. Sulfur becomes S-2. So this should start helping you to recognize some patterns and some predictable ions. So the example that we did in class is to tell how many valence electrons are in phosphorus. Draw its Lewis dot diagram. And predict its ion. Predict the ion it makes. Okay, so the first thing that you have to ask yourself is, what is phosphorus's symbol? So you can find it on the periodic table. Phosphorus is a capital P. And when you look it up on the periodic table, it is in group 15, which is also known as group 5A. And all of the group 5A elements have 5 valence electrons in them. So in order to turn this into a Lewis dot diagram, I am going to need to draw 5 dots around it. And then we ask ourselves, is this stable right now? No, it is not, because if it were stable, it would have a full octet of electrons. So it has 5 dots and it needs to get to 8. It could gain 3 electrons in order to get to 8, or it could lose the 5 electrons that it already has, and then it would default to the next inner shell, which would be filled. So you have to ask yourself, what do you think is easier to do, to gain 3 electrons or to lose 5? Well, gaining 3 seems easier than losing 5, because 5 is more. So if I pick up 3 electrons, then phosphorus now will have all 8 electrons around it, but I have to put a -3 charge on it because it has gained 3 more electrons. It's become more negative by 3. So the ion would be P-3, and we would call that the phosphide ion, because we take negative ions and add IDE to them so that they are named properly. I hope this has helped you to understand Lewis dot diagrams a little bit better and how to predict what ions will